So I will go a few questions on like neural networks and discuss some concepts in CNNs today. So here, suppose we have a simple function. So what is a perceptron function? Can someone tell me? So we have an input x, and then you pass it through a perceptron, and then you get an output, right? Say I have f of x. So what is f of x equal to? So it has a vector w, and it takes the input x.
It is 1 if x greater than equal to 0 and 0.
Greater than, what is greater than equal to 0?
If the summation with x into
W transpose
equal
x.
to actually threshold.
So first thing is the function is w transpose x, and then you put to, if you want to classify them into one of them, then you threshold this as greater than or equal to 0 or so on, right? Like that would be my prediction. Like say my y cap is 1 if w transpose x is greater than or equal to 0, otherwise 0, something like that, right? That is how it do a simple classification function. So yeah, I have so here what would the output of this perceptron be? Like w transpose of the function at this point, not the final threshold for this vector. So I have w, which is 0. 0.6, 1.5, minus 0.4 and 0.8, right? And then my x is 0.5, minus 0.7, 0.9 and 0.3. Fine, let's just say you get, I don't know what the exact value. Okay, what is it? Okay, it's apparently minus 0.87. So now I want to compute the derivative of tan h of this function, say z. So I want to do d by dz of tan h. So what is the derivative of tan h? And why is this like, why am I interested in this function tan h?
Tan h is a activation function.
Right, it's an activation function which we use in neural networks, right? So that is a key feature of neural networks, right? Which is that is I want to introduce non-linearities in order to learn complex functions, right? So yeah, it's an activation function. Yes. How does it look like? It looks something like this. It goes from -1 to 1. What are the other activation functions you are aware of? Can you name a few? Non-linearities. ReLU, right? And ReLU would look like, it's this, right? It's 0 on the left side, the negative part, and it's a linear function. Sigmoid, yes. So sigmoid also looks like, I mean, sigmoid and tan h look very similar, but the range of sigmoid is 0 to 1, and at 0 it is 0.5. Any more? Anyway, these are like the main ones, and then there are many other, yeah, e-ReLU, so many versions of ReLU, like leaky ReLU, e-ReLU, and yeah, and like NLP and all, they use something else. I forgot the names, but yeah, uh, yes. So yeah, anyway, so the derivative of a tan function is given by 1 minus tan h square z. So if I know what tan h of z, I just put this value of z in this and substitute it here, I would get this value. So which of these statements are true about the dropout function which are used in neural networks? Dropout during training causes the network to overfit because it randomly drops neurons, making the model too simple. Is this statement true? What is the use of dropout? Regularization, right? So by regularization, what am I trying to achieve? To prevent overfitting generalization, yes. Yeah, so naturally, I mean, neural networks can end up learning very complex functions, right, which may not generalize to um, my test data or yeah. So in order to avoid neural networks overfitting the training data, we do this dropout where we randomly skip some neutrons and compute the output so that it does not rely on every single neuron's output when it's finding the, I mean, getting the output feature. So in that sense, I'm like trying to model simpler functions using the same network, which, so that is why this is false. So it does not cause, it prevents overfitting, right? Then, so during training with dropout, the network adjusts the activation levels so that the outputs remain consistent when the dropout is not applied during inference. Is this right? Adjust meaning doing some sort of scaling on the output. Uh, say I have z is equal to f of x with weights w, and adjust by some factor, say gamma. So does dropout do something like this? If so, why is it required? Okay, so suppose I've used dropout during training. During testing, do we use dropout or not? Is it a strategy for training which have to? Okay, no dropout during inference, right? So if there is no dropout during inference, that means that I'm using all the nodes in the network, right? Like all the neurons. But while training, I wouldn't be using all the neurons. So because say I'm using only 70% of the neurons while training, and while testing I'm using all 100% of the neurons. Would that like cause some discrepancy because I'm not using all of them? How do I avoid it? If it is? So suppose like on like the expected value of each neuron, say that what f1 of x, say w1 whatever, uh, is say 0.5. Okay, so each neuron on an average gives out a value like 0.5. Suppose I'm using 70% of the neurons only, so I'm doing this on 70%, right? So y is equal to f of x, which is a combination of all such neurons, but then I'm using only 70% of them. So I would actually be using only like the expectation of my output function would be 0.7 into 0.5, which is 0.35. But then when I'm doing testing, I will use all the neurons, right? So the expectation of my output function would be 0.5 itself. But there is a discrepancy here, right? While training, it has seen the neuron has produced an average output value of 0.35, but while testing, it will produce an average value of 0.5. So to avoid that, this neuron, the input neuron, is scaled. it is scaled by the 1 by the dropout ratio, as in, so whatever my output is, it is scaled by 1 by 0.7, so that on average it produces the same expectation. So that is why this gamma is defined by 1 by the dropout rate. So during training with dropout, the network actually adjusts the activation levels so that the outputs remain consistent when the dropout is not applied during inference. So this is true. So what is the third statement? Dropout during training leads to a smaller final model size, as some connections are permanently remote. Is this true? So just because I'm using 70% of the neurons, does that mean I'm making the model smaller? Also, will I be dropping out the same neurons all the time or different neurons? Like in each pass? Different neurons, right? So like in the first time, say I would have dropped neuron first, third and fifth. In the second time I would have dropped maybe second, fourth and sixth and so on, right? So it is not, that means I still need all the neurons. So I'm not actually reducing the model size, I only use um, a subset of the neurons to do my forward pass, but that doesn't mean I'm reducing the model size, right? So this is false. The final output during training when dropout is applied is multiplied by the dropout rate to maintain the expected output when dropout is not applied during inference. Is this true? It's not, no. It is not multiplied by the dropout rate, it will be 1 by that, right? As I explained earlier for the statement 2. So is this clear? Do you have any questions on how dropout functions? Okay. So suppose you are training a neural network using mix-up augmentation. Then we have two samples, x1, y1 and x2, y2. So x1 is a vector, y1 is a target I have, which I mean target labels, x2 is a vector, y2 is again the target labels. It's a two-class classification problem. Now we are given the mix-up hyperparameter to be 0.3. So how do we calculate this mix-up augmented sample? So the mix-up augmented sample is calculated as lambda into x1 plus 1 minus lambda into x2. Similarly, the target is also calculated as lambda y1 plus 1 minus lambda y2. Right? So what this does is, like, suppose I have data samples here and here. Say this is of the other class. So what mixup does is it tries to linearly interpolate between these two samples, like any two samples which you pick, and you interpolate between them, and you also give a probability of with what probability it belongs to a particular class. So suppose I pick a sample here, like which is in between here with probability 0.5, then I teach the model to say it is of class 1 with probability 0.5 and class 2 with probability 0.5. Say in this case 0.3. So I would have done like my y mix would actually be 0.3 into y1, which is 1 0, plus 1 minus 0.3 is 0.7 into y2, which is equal to 0.3 and 0.7. So this is my target label for my augmented sample. So I'm saying I'm asking the model to learn not just like binary classifying what a class means, but to also say it looks something like with 0.3 probability it looks like class 1 and 0.7 probability this augmented sample looks like class 2. So now suppose I have a neural network which is defined like this: W2 into W2 of G of W1 of X. X is our input and F of W comma X is our output. Now I use a cross entropy loss and to train this model. It's a classification task. So I have two weight vectors W1 and W2 which I have initialized to 0. Now will the network be able to learn anything? So this is my initialization, right? Now I use gradient descent and I update the weight vectors. Will the weight vectors change? Like will the model be able to learn, or is there something wrong with this scheme here which I have to take care of? It's like, what is there any flaw in this design? Model will not learn. Yes, it will not learn, but why is that so? So which part of the statement is not is making the model not learn? Like the design of the neural network here, or using cross entropy loss, initializing of weights, or having what like the okay tan h as non-linearity. So which of these four? So there are four statements here. Which is the statement that is causing this, this problem? Initializing weights to 0, right? So why does this initializing weights to 0 not make the network learn? um, so how do I, in gradient descent, how do I do my weight updates? So this is W1. So like I start from W1 and I take, a step in the direction of the gradient, right? So L is my loss function and with respect to W1. So this is my gradient step update. Now how do I compute what W1 is? So the weight will not change when this term is 0, right? Like W1, when the so if only weight W1 won't change if dou L by dou W1 is 0. So how? Okay, I have X. First I pass it through weights W1. I get W1X. Then I pass it through G, which is what, tan H here. So tan H of W1X, and then I pass it through W2, which will be W2 transpose tan H of W1 comma X. Then I have loss from that would be my output, which I use to compute my loss. So how do I back propagate the gradients here? So I call this as Z1. So this is Z1 here. Uh, So first I would calculate, so z1 is a function of w1, right? So with respect to the loss, I would first, okay, let me call this z1 and this z2. So the first step is I would calculate the loss with respect to z2, right? If I want to compute dou L with dou 1, w1 with z2, and then z2 is a function of z1, so I do this, and then z1 is a function of x, so I do this. So this is the back propagation I'm doing here, right? Now at which of the steps this will become 0? What is this term? dz1 by dx, that is d of, yeah, this is w1 transpose x by x, right, which is w1. So I have three terms here, z2, z2 by z1 dot, then this term is w1, but then I have initialized my w1 to 0, so this term becomes 0, making dou L by w1 equal to 0, meaning that weight w1 doesn't change, right? Yeah, so in a similar sense we can find the gradients with respect to w2 and also establish that it doesn't change. Okay. So how many of you are aware of PyTorch and used it at some point? PyTorch, Python, NumPy. How many of you have used Python? Like you can raise your hands. Okay. Okay. Only two of you have used. Have you guys used PyTorch as well? Okay. Fine. Uh, so this notebook gives a quick intro to the basics of PyTorch and like NumPy as well to some extent. So in neural networks, the most common operations like which we use is actually max. They're called multiplication and additions, right? So all like the fundamental operations in any neural network is actually doing this W transpose X plus bias, right? This term, which is called on and on again and again in any sort of network. So PyTorch is specially written so that it is written so that it can leverage this parallel processing of GPUs to run the neural networks faster. So it has like this is how you create tensors from here, like the list, pass a list, create a tensor. So that fundamental element, that is the arrays, which could be your inputs, weights, biases, any of this is basically a matrix, right? Matrix or a vector, which are all represented in the form of tensors. So yeah, these are some simple tensors which are created, and there are several functions like, suppose I want to sample, I get a three-dimensional vector from a uniform distribution. I can use this function. Sampling from a random distribution of matrix of size 3 cross 4, creating a zero matrix, random matrix, which is of the same dimension as A. So this is what it says. Zeros like meaning it will take the shape of A, but it puts the all zeros. Rand like meaning it will take the shape of C, but it will put I mean uniformly samples, I mean numbers sampled from uniform distribution here. So yeah, this the any random number generator uh, is actually, you set a seed, and based on the seed set it generates a certain random numbers. So this is like very important if you have to, replicate results, right, over different runs. If each time if it starts sampling something different, it obviously it will sample something different. um, then I might not be able to replicate my results. As in, so I have a database of 10,000 samples. In each batch, I would be sampling say 10 samples, right? So one time I do this training, I might get some number. Again, I don't change anything in the code. I run the exact same algorithm again. I might get something different, right, slightly, and that is because different samples might be sampled, right, in each batch. So to ensure reproducibility, which to help, I mean, which will help you debug, understand what is happening. It's a very common practice to set this seed so that each time you run the code, your results are reproducible. So here I see this, right now. Suppose I change I change the seed, but there's nothing about this, right? I'm still simply um, yeah. Now these tensors are different from what I got here, right? Because these are random numbers sampled. But suppose I set the same seed and run, I'll be getting the exact same random numbers. Yeah, it has all these functions, numpy like functions like arrange, linspace, to create like linearly spaced elements, and yeah, and other functions like addition, multiply, matrix multiplication, dot products. All these things are also there. Yeah, you can do all like element wise additions, subtractions by simply writing it in this way. uh, and these summing functions like taking sum, mean, min, max of a vector. Like I'm in, suppose when I want to calculate loss, I would have calculate loss for each element in the sample. I mean, say there are 10 samples in my batch. For each element, I would have calculated the loss, and I could just sum them using this kind of functions, sum or mean. And yeah, like this is the most common operation, right? As I said, like W transpose X plus B. So yeah, there are two ways you can do this. One is using this matmul, and also you can use the at the rate symbol, which does matrix multiplication. If you want dot product like this, dot product of two vectors, then you can use torch dot dot. Yeah, and this is how you access the different like subsets of a tensor element. Yeah, and then there are these functions which uh, so I want to flatten a 2D 3D array into a one dimensional array and then reshape it back to different dimensions, say dash 12 elements, and originally it was of the shape 6 comma 2. Now I have flattened it to make it a 12 dimensional vector, and then I want to put it back in the form 3 comma 4. You can do all such operations. And then squeezing, so suppose I have one dimension dimension with size 1 only. So it's essentially it's a 10D vector, right? So you can squeeze that one dimension and just get a 10D vector. And you can also do the other way. If I want to insert another dimension, and so on, permuting different axes. Yeah, so this is an example. Like I have a color image where the first dimension is the color, then I have height and width. But then, like there are like different image libraries to read the image can be reading them in different ways, right? It's like there's OpenCV, there's SKImage and other libraries, right? So they would read it in different forms, and I would want to put them in the correct order based on the need. So here if I want to permute this tensor so that the first dimension is height, then width, and the last dimension is the color. So how I pick that is, so here one if I take the dimension index, it's 0 1 2. 0 dimension is channel, right? Yeah, color. So and I want color to go to the last one, so 0 goes here, and I want height to be the first dimension. So here the index is 1, 1 comes here, then width, and then channel. So whatever was if the dimension 3, 48 and 64, now it becomes 48, 64 and 3. So now suppose I want the other say I want to do this instead. Color width, color and height. So what would these indices be? Here permuting. So my what would the target shape be? If input shape is this, what should my target shape be if I were to rearrange it in this way? Can someone tell? Hello, you can hear me, right? Two zero one. So it would be 2 2 first because I want width to come first, then the color, and this is here, right? Yes. So yeah, I first have width 64, then the color, and 48 is my height. Yeah, you can do transpose of a matrix using dot t. This concatenate two matrices. Like I have two vectors x and y. Now I can concatenate them. Yeah, so I have this x is of dimension 3 comma 4. Then here what is the dimension? It is 3 comma 4. Now if I concatenate them along rows, what should the dimension be? So what should the dimension be if I concatenate them along rows x and y? What do you expect here? What is the height and what is the width of that matrix after concatenation along rows? So by concatenating along rows, I'm meaning, so I have the first 3 rows, and then along rows I append the other rows also, right, from the second matrix. So there are 3 rows and then 3 rows in the second matrix. So it would be, and I preserve the columns. So it would be 6, 4. Here I'm preserving the columns. So I'll have concatenate along columns. So I will have 3 rows, but I'll have 8 columns, right? Yeah. By rows it would be 6, 4. By columns it would be 3, 8. Yeah, and these are the ways you can convert from like a tensor to array, array to tensor, and so on. Yeah, so by default, when we create a tensor, it would not be on a GPU. Even though there is a GPU on your system, it won't be. So if you check on what device this tensor is stored, it shows CPU. And you can make, like, put that tensor to, so I checked if, so this is how you check if you have access to a GPU in your machine, on an NVIDIA GPU. It says it is available. So here we'll set the device as CUDA. Now once you set the device, so I would have got like device to be equal to this string CUDA if it is available. Now whenever I create a tensor or I load a model, so unless you copy that model to the device, it would only be on your CPU. So before you run, you always ensure that you put your models, tensors, inputs, everything you are dealing with onto the GPU and run. Only then you would be able to run it really fast, right? So here we put this, yeah. So originally, like, this was the tensor created, and when we check what is the device of this tensor, it says CPU and its type is torch.float tensor. So once I put it to the device, which is GPU, then it shows the device to be CUDA 0. So 0 indicates the index of the GPU. Like, say I have 3 GPUs, 0 will be the first GPU axis which I'm accessing, and it's of the type CUDA float tensor. Yeah, you cannot combine like different data types together. Like, you have to cast one type to another if you want to use both of 2 tensors and operate on them. So in this notebook, we'll see how to build a simple perceptron on a simple toy dataset which is synthesized. So here we're loading a dataset, like a toy dataset here, which is 2-dimensional. Yeah, so x and y are your data coordinates. And so how many data points do you have? Yeah, it looks like we have 100 data points, and belonging to 2 different classes, 50 of them to class 0, 50 of them to class 1. So we load them, shuffle the data set, and then take like 70% of them as training data set, and like 70 samples for training and 30 samples for testing. And then here we do data normalization. So I get the training data, compute its mean and standard deviation. Using that, I do the mean variance normalization here. So why do we do, so in here what are we doing? So there are, we're like the first line in this line here is getting how many data points I have, and then this is like my seed, and I am shuffling this, like creating a random so I have 100 samples, so 0 to 100 I'm shuffling the number 0 to 100 so that they're randomly shuffled, and then I fetch them so that I've shuffled my data. So why am I doing this process? What if I don't do you think the neural network would learn fine if I don't shuffle the data? So suppose my y labels, the first 50 samples come from class 0 and the last 50 comes from class 1, and I keep going one sample after the other, or say even in batches I go I take 5 samples at a time, compute loss, update it, the next 5 samples, and so on. So I do this process. When I do this kind of learning, whether I shuffle the data or not, does it matter? So this is how the data set here looks like. We've just visualized them, right? It's a two-dimensional 2D data, and 50 samples from, okay, this is the training set, so there are like 70 samples belonging to class 0 and 70 belonging to class 1. Now suppose I have not shuffled it. How some classes would entirely go into the test set if data is not shuffled. Okay, fine, maybe that's the case. So in that case what would happen, I have 50 and I've taken 70 samples, right? So I would have in my training set, I would have 50 samples from class 0 and 30 samples from class 1, or forget it, in this case I have a separate test set where I have all the classes. It doesn't matter. Like I use only this 100 samples for training, and I have a separate 50 samples for testing. So in testing I have all samples, both class 0, class 1, and in training also I have all of them. So I'm using all 100 but in the same order. So what would happen in that case? So what is the goal of the task here? I want to distinguish class 0 and class 1, right? Basically I want to learn like identify a linear classifier here in this case that separates class 0 and class 1, right? That is the goal. If I go through them in the same order, that is I visit this sample, so I visit all the blue samples first and then I go to the orange samples. In that case, would I be learning a classifier or not? So I have to predict a 0 for this, 1 for this. The model would get biased in this case, right? How do you define bias? Like what do you mean by bias?
So the model initially thinks that all the things that come in the first, all the inputs that are given in the first initial things are all class 1 and the remaining are all class 2. So it tries to learn some pattern like this, which is not true actually.
Yeah, so I want to predict like 0 for all the blue samples, right here. So there's nothing to learn. It would, I pick any random line, like say any line, say like x equal to 1, right? Like a vertical line here. and even that is enough, right? As long as I'm doing this, going over each of the sample, it can just say it is 0. Like that's a very simple classifier to learn. It could be x is equal to 1, x is equal to 2, x is equal to 3, anything. All of them satisfy this. So it's not really learning to distinguish. But when I come start visiting these samples, that is when I start getting errors. So at that time, I'm asking the model to predict 1 for this, right? What would it do? It's a very simple fix. So earlier, suppose the classifier was x is equal to 1. Now it will just move it to x is equal to 0 or x is equal to minus 1. And now the error for all these orange samples will be 0. So in the starting, I would have a classifier say at x is equal to 1. Once I start visiting class 1 samples, the classifier gets shifted to say x is equal to minus 1. So at the end, I would have a classifier as x is equal to minus 1, a line, vertical line here, which is not at all distinguishing both of them, right? So it's actually not learning anything at all. So I have to ensure in each batch, or I need to show both the samples simultaneously, so that like if I have 5 samples from here and 5 samples from here, then it learns to distinguish both of them. Otherwise, I'm not actually making the model learn anything at all if I don't shuffle the samples. Is that clear? Like intuitively, do you understand why shuffling is important? Okay. In uh, like say you guys are interviewing somewhere, and this is such a trivial question, like when you're reading through this nowadays it's very easy to build small models, right? If someone is given a task to build a simple classifier like on to distinguish digits, cat dog classifier, all these things, anyone can write code very easily with the help of GPT and so on, and then talk about it. But so how do you actually test what someone knows is by asking such very simplistic questions. This is something I'm telling from my experience. Yeah, like when we are hiring say IAS or someone, we do this, give a task, simple task, and then everyone submits very nice notebooks. Uh, and I've observed that we have asked, like in the very first block of code, when we asked them to explain what they've written, most people were not able to answer why shuffling is important at all, which is kind of sad. Yeah, yeah. So just saying, you should like focus on learning the basics also, always, irrespective of what the most advanced tools being present right now. Yeah, this is how the test set looks. So to define a simple perceptron model, so what are the components of a perceptron? I have one like weight vector, like I need to know the data dimension, and then so the function is w transpose x plus b, and then I do some thresholding, right? So I define the weights like initialize weights, which is of dimension whatever the feature size is. So it's 2D here, so the number of features is 2 comma 1, and then there is a bias vector. So what am I doing? W transpose x plus the bias. So it's a simple single neuron here. So it's just one neuron. So the bias dimension is 1. It's a single neuron. And what is the function? I'm doing w transpose x plus b, right? So the dot product does a w transpose x, right? So self dot weights, I pass the input plus add the bias, and then my predictions are thresholding. So if the w transpose x is greater than 0, I predict 1, otherwise I predict 0. So this is my forward pass. So what is the so this is how I initialize the model, and then when I'm back, while learning I also want to do backward pass, right? So I first forward pass the model, pass the input, like get my predictions, then I compute the error, which is this is my target minus what the model has predicted. So I compute this, that is my error, and I use that error to do back propagation over the weights. So in a perceptron model, the weight update is actually given by yeah, like you either add the sample or subtract the sample, right? Like w, the delta w is actually x of k, like the input sample. So yeah, I iterate over the samples, I compute the error, and then I update my weights and biases. Then when I'm evaluating the model, I just pass through it, do the forward pass, get the predictions, and then to compute the accuracy I check how many of the predictions are actually correct. So I do np dot sum of like predictions equal to y and divided by the number of samples. So this is my simple perceptron model. So here I'm creating a perceptron model, first one, and then I train them passing the x-train, like the 70 samples which I sampled earlier, right? Pass them, and the learnt model is this. So it's a 2D, like it's a simple, I mean, it's the equation of line which I'm learning, right? So I have these weights and this bias. Then I evaluate the model. On the training data, the train set accuracy is 100%. It's a simple data set here, right? All it has to learn like a line that separates. This is linearly separable data, so I can learn a perfect classifier here. Then I test it. On the test data, I have an accuracy of 93.33%. Then let's see how the decision boundary looks like. So this is my training data and the classifier learned here, right? Which perfectly separates my 0 and class 0 and class 1. But this is how my test data looks. Here it has misclassified these two samples here, right? And wrongly predicted as class 0, which is why I have the error. So this is the same. So this class was defined using simple numpy functions, right? There's no torch functions used. So here the same thing is implemented using torch. Pretty much the same, where the numpy functions are replaced by creating torch tensors, and this is the dot product done. Instead of np dot where we have torch dot where. Yeah, it's pretty much the same in this simple function. But this would run much faster than the other one. Yeah, this is a deterministic logic, right? The rule is fixed. If it's a positive sample and misclassified, then I do plus. Otherwise, plus x off, plus adding the sample to the weight. Otherwise, I subtract the sample so that the dot product is reduced. So you guys are familiar with the backpropagation and chain rule, everything. can I just go over the notebook, or do you want me to like briefly review the backpropagation algorithm? Sorry. So here we'll see how the gradients look like for this function. So yeah, suppose these are my inputs. It could be the data vector or the weights. So z is equal to sine of x square plus y square. So the gradient vector dou z I define is with respect to my input variables dou z by dou x and dou z by dou y, which I would need during backpropagation. So by yeah, so this is my input, right, x. I'm passing through the function h, and then I'm computing the gradient. So now if I have need the gradients of f with respect to the variable x, so I, in using the chain rule, firstly I would get the gradients of this function, like g with respect to its inputs. Like the input for g is the function h, right? So I get dou g by dg by dh, and then the internal function dh by dx. So in a similar sense, if for this function z is equal to f of uh, g of xy, so f of u, the inner function u, is equal to sine u, right? Yeah, so firstly I would do df by dou f by dou g, and then dou g by dou x. So the first derivative is so I have sine u, the derivative of that is cos, so I have cos of that function, which is g of x comma y, and then the derivative of g of xy with x square plus y square. The derivative with respect to x is 2x. So the derivative of z with respect to x is cos of x square plus y square into 2x. Similarly, for with respect to y, I have cos of x square plus y square into 2y. So to visualize how the gradients of this function is, we'll define the function and its gradient. So if I give xy, I get the function that is sine of x square plus y square. I compute at all the xy points, and then the derivative function is 2x into cos of that with respect to x, and with respect to y it is 2y into cos of that, right? And I return this vector dou z by dou x and dz by dx and dz by dy, and then I plot how it looks like, how the function looks like, and how the gradient looks like. So this is how the function looks like, and these are the gradient vectors. So this is it's a curve, right, like sine curve, which goes up and down and so on. So that is why these gradients point in different directions. So yeah, when I'm going from like purple towards the yellow region, the gradients show in this direction where it is increasing. Here it shows the other way, right, the decreasing gradient. So this is a counter plot of that. So in gradient descent, if you have to update the vectors, what we do is at each step we compute its gradient and take a step of like so how big a step is determined by this learning rate, right? So or the step size, which we call eta. And so starting from that point, I take a step of size eta in the direction uh, dou f at the which is computed at that particular point. Yeah, so this is how I have a simple function, right? So I start with an initial random guess or randomly initialized weights, and then a step size and a particular number of steps, or even or any other stopping criterion, like when my loss has become negligible, it has come under some threshold or something like that. So I keep iterating over it and I keep updating weights in this form. And what is this function usually? It is the law, what we call as the loss function, right? Like we measure the loss with respect to of the predicted predictions with respect to its true value, and so I want to take a step in the direction that minimizes my final loss. So always compute this. This is the direction in which I want to move each weight vector, where I am reducing the loss. That is why the negative term comes here. So in Torch, how this is done is I build a computation graph in the forward pass, which keeps track of all the parameters and operations in the forward pass. And when I'm doing back prop, yeah, it based on the graph it has built, it will calculate the gradients and pass it back in the direction it's built. So this is what a simple perceptron function here, where they have defined W transpose X plus B, and a simple neural network with non-linearity tan H, and I've used mean square error loss, where that is I pass the prediction and true value, I compute the difference, take the mean of the square of that, which is my mean square error function. So suppose I have input features and my target vectors, I pass them through the forward, do forward pass through it, compute the loss with respect to that, and then now I back propagate that loss. Yeah. Yeah, so the backward pass is usually done by calling this function. So I call, like, whatever is my loss, and I call the backward, which will basically trace through the computation graph from the end point from my loss function to the input stage, and then update each of those vectors. So this is what is automatically computed using this PyTorch AutoGrad functions, and this is like the analytical gradients computed manually, and by checking them we see that both of them are equal. So this is how a simple neural network is defined and trained from scratch. So in this week's lectures, you were introduced to CNNs, right? So can someone tell me what CNNs are, where are they used, how do they differ from feed-forward neural networks? They are majorly used for visual applications, right? So what was the drawback of using feed forward neural networks for vision applications? Vision applications meaning using for images, videos, such things, right? So you can unmute and answer. Large number of learnable parameters. So what is the order of these learnable parameters? So suppose I have a so suppose I have a HD image, and I want to build a neural network over this. Say it's a say a full HD image is of size what, like 1980 cross 1920 cross 1080 pixels. So the number of neurons I would need to process an image is of the order of the height and width of that height into width of the image, right? Which is like really really huge. So yeah, image is extremely high dimensional data, and it is practically not possible to process a fully connected feed forward neural network that like flattening the whole image pixels and building it. But then that is not actually how we look at images also, right? It's not like we scan through the pixels together. We look at an image locally and see what is happening. Like there is eye at some a particular place in the image here somewhere, and then so we locally process information and combine them, and then understand that this means a cat, right? So CNNs were designed to induce this natural bias of images. So yeah, if you have a 200 crush 200 images, we would need 40k hidden units. That becomes equal to having 2 billion parameters, which is like really really huge. And even after doing all of this, we're not really processing information locally how we pursue as images as humans, right? So yeah, it's anyway not required. So CNNs are designed so that it looks at local regions, and so initially we look at local regions as a 3 cross 3 windows and so on, and we keep pulling this information to in a to understand what is there in image in a hierarchical manner. Once I extract features in this manner towards the end and like reduce my dimension, so starting from 200 cross 200, I would have come down to say 8 cross 8 or 4 cross 4 spatial dimension. Then I can flatten them so that it's a reasonable dimension which I can process and use that as my final feature vector to pass it to a fully connected layer to learn a classifier, suppose, in a classification application and so on. So how is so this is how convolution operation is done, right? So suppose yeah, here for example my input is of size 6 cross 6 and my filter dimension is 3 cross 3. So I pass the filter, I scan through them in a raster manner and get this output, right? So I have 6 cross 3 6 input, 3 cross 3 input, and what is my output dimension? It is 4 here, right? So yeah, it is 4 here. So suppose I have a 2 cross 2 filter here, what would the output dimension be? 6 cross 6 input and 2 cross 2 uh, filter dimension. What is the output be? Anyone?
It will be 5 cross 5.
It will be 5 cross 5, right? Yeah. So I'll go with this second element, third one, fourth one, and fifth one. So it will be 5 cross 5. And so what would the dimension of the filter be usually? So suppose my image is of size 32 cross 32 and I have 3 channels, which is the RGB dimensions, right? Color channels. So the filters, so 5 cross 5 is my spatial dimension, and the depth of the filter is always equal to the input number of channels. So I have 3 channels here, right? So the depth of the filter is 3 here. So I would move this 5 cross 5 cross 3 filter on this input image to get one output. So the number of like operations I am doing to get one output here is over one convolution operation is 5 cross 5 into 3, right? These many multiplications I am doing, and then adding one bias term. So yeah, it is 25 into 3, 75 dimensional. So at one spatial like local region, so I need 75 multiplications and one addition to get my output at one. And totally how many such operations would I be doing here? So this is my input size and this is the filter size. So what would my output dimension be? So space, yeah, I'll get one output channel. So spatially what would the dimension be? So how do you compute what the output dimension will be based on my input size and filter size?
In this case, we do 32 minus 5 minus 4 actually, which is kernel dimension minus 1.
Yeah, so it is actually 32 minus kernel dimension.
4.
Yeah, minus of kernel dimension 1. So it is 32 minus 5 plus 1 usually. 32 minus whatever kernel dimension plus 1. So we get 28 cross 28 activation map. So yeah, this is the result of one filter, and I would use a lot of such filters, right? So each filter could be understanding something very different. One filter could be doing edge detection, filter could be doing say color detection, detecting blobs, like very local features, right, from images. So in order to extract different kinds of information from the same input, we make use of, we learn different filters, different number of filters. So yeah, I have one activation map, then I do the same thing, the same operation, but then the weights would be initialized differently. So by initializing weights differently, they'll learn something differently. But suppose if I initialize all the weights like 5 cross 5 cross 3 filters to be the exact same thing, they end up learning the same. So there's redundancy, and I'm not extracting new information by having different activation maps. So I should always ensure, when initializing, each filter is something different, differently initialized, so that they learn different attributes from the image. So I keep doing this and extract my activation maps. So I start from 32 cross 32 cross 3 input, and suppose I have 6 5 cross 5 filters. The output features dimension would be 28 cross 28 spatially, and 6 is the channel dimension. So you stack these convolution layers and also introduce non-linearities at each stage and stack them up to build a convolutional neural network. So yeah, if I have a input dimension of 7 cross 7 and I use stride 3, so I can do 3 cross 3 here, and by stride 3 I'm shifting by 3 pixels to compute the next input, right? So I get 2 values, but then to shift another time I don't have any pixels left over here, right, to compute my output. In that case, if I ignore, I'm actually ignoring information in the last column, which is also not desirable. So how do we fix this? So like the normal strategy used is to zero pad the images. So how many ever pixels I am falling short of, I pad it with that much for that filter size. So it's a 3x3 filter. So 3x3 filter with stride 3 suppose. So I would pad uh, like 2 pixels in the horizontal and vertical direction. One on the left, one on the right, to be symmetric. So this is what we do to do zero padding, which is primarily done to maintain the spatial dimension. So if I want to use stride 1, that is just shifted by 1 pixel and so on, but still preserve my output dimension, right? So here what we saw is from 32 we came down to 28, but I don't want to do that. I want to preserve my spatial dimension. For that I do extra padding so that I preserve my spatial dimension. So here, to retain it as 32, how many pixels should I pad? I would have to pad 2 in each direction, right? Left, right, top, bottom. So anyway, yeah. So suppose this is my input, and then this is how my filter is defined. I have k filters, and the special filter size is f, and I'm moving them with stride s. The amount of zero padding I want to add is p. The output volume W2H2D2 is given by this. So W minus F plus 2P. Earlier, what we do, like it was width minus the filter size plus 1, we did that, right, to get whatever my output was. But then here I'm also adding padding, right? So my input sort of is enlarged. So I have like W1 plus 2P minus the filter size, and S divides the stride, like at what rate I'm moving the filter, plus 1. So this is how my width and height is. The output number of the output channel dimension is equal to the number of filters, right? Here we did use how many, like 6 filters, right? So 6 filters we did, so the channel dimension is 6. So d2, which is the depth, is actually the number of filters. So what is the of one, so this is what this represents one convolution layer, right? Which takes in the input of this size and has these many filters. So the number of weights in one convolution layer is given by the filter dimensions, right? So it would be the number of filters k into the spatial extent, that is f, like width and height of the kernel, that is f into f, and the depth of it, how many filters do I have, which is so if my input I have d1 is my okay, yeah. So each filter is defined by f into d1, right? F into d1 is the filter dimension, and I have k such filters. And for k such filters, I have k biases. So this is the total number of weights a convolution represent. That describe a convolutional layer. So yeah, we do this convolution, like we have 32 cross 32 input, we preserve and get a 32 cross 32 output. But then, like, so I start with say 200 cross 200 images. I don't want to keep continuing doing preserving the dimension, right? I want to reduce the dimension so that I can finally use a fully connected layer and operate over it. So how do we reduce the spatial dimension? We use these layers called pooling layers, which is there are different types of pooling layers like max pool, average pool, and so on. So which is again like a filter, but not exactly that. It's not. It doesn't satisfy the properties of convolution and all. So suppose I have a 2 cross 2 filter, max pooling filter, I just move it over the input, and in that band I see what is the maximum value within that 2 cross 2, and that becomes my output. So if I have a 2 cross 2 filter, so I'm reducing the spatial dimension by 2, right? Of 4 values, I'm just picking one value in both dimensions. So starting from a 6 by 6 input feature map, I reduce it to 3 cross 3 input. So this is how I downsample my feature maps. Yeah, in max pooling I get the max, in average pooling I compute the average of the 4 input elements. So once we do this, we would have say, I mean, I start from say 200 cross 200. I've come down to 6 cross 6 to max pooling. I've got a 3 cross 3 feature map, which represents the whole image, right? Like whatever is in 200 cross 200, I've somehow captured in a spatial region of say 3 cross 3, and I would have say n number of channels. So starting from 3, you usually can go up till 64, 128 channels and so on. But still, the dimension is much lesser here. Like 200 cross 200 cross 3 comes down to 3 cross 3 3 cross 3 into say 64. So even if I have like 64 128 filters also, um, its dimension is much lesser than the input image being flattened. So I flatten this final feature vector this way, and then I pass it through a feed forward neural network to give my final get my final predictions. Like say if I want to learn a classifier. So yeah, this is how typical convolution layers look like. Extracting different types of features, different types of edges, directions, it detects like colors and so on at different layers, and finally it compresses all that spatial information, and based on this last layer, it gives out the predictions. So this structure of convolution design of convolutional neural networks is what we call as inductive bias. That is first looking at local regions and then looking at global regions, like in a hierarchical manner. We're imposing that structure and making the network look at it in that way. So when we design networks with a particular strategy, like we're inducing a bias in the network, as in how designing, like instructing how to see the inputs. So why are CNNs better than fully connected networks for image data? Both of them are true, right? We just discussed it as parameter efficient because we can't really build fully connected neural networks for images directly, and also for having this inductive bias. So yeah, a simple exercise for you guys. If this is my input size and I have a 5 cross 5 filter, I use 3 such filters with stride 2 and 0 padding. So what is the size of the output filter? Can can you take a minute, solve this and tell me what the output size would be?
31 cross 30.
What? 31 cross?
31 cross 3.
Why 30? Okay.
Like maybe it's some rounding of. We actually get it as 30.5.
Huh, 30.5 and you round it down or up. So this is 64 and it is 5 cross 5 filter, so K is 5 here, and padding is 0, so this is 0 padded. Stride is 2, so it would be 64 minus 5 by 2, right, plus 1. And how many such filters? So the number of channels is defined by the number of filters we are using. So we are using 3 filters. So let this. So what are the benefits of using pooling layer? So are we uh, reducing the number of parameters in the network by using these pooling layers? By the way, do pooling layers have any weights? Hmm?
They don't have any weights.
They don't have any weights, right? Yes. And yeah, so are we reducing the number of parameters in the whole network if we have pooling layers?
Yes.
Yes, right? So we're reducing the feature dimensions by using pooling layers. So initially, say I'm operating over. Okay, that's not necessarily true in the convolutional part, at least. Uh, yeah, so the weights of the convolutional layers are not really reduced, but because the weights of convolution layers are those 3 cross 3 filters which I designed, right? It doesn't matter if I have 200 cross 200 images or 100 cross 100 images, I can still have 3 cross 3 filters, 3 cross 3 into input dimension filters. But then where am I actually reducing the weights? In the final part, right? Like here, this part, this is where my weights get reduced, like when I'm building this fully connected I mean the feed forward network. But in the convolutional part here, in this part, even if I don't have pooling layers, I'm not, it doesn't matter like what the weights are, right? I'm not reducing uh, the number of parameters, because irrespective of 28 cross 28 or 32 cross 32, I can still use 5 cross 5 filters. Does that make sense? Okay, another question I'll just ask. Yeah, I think that was pretty much what I covered. Okay. Yeah, in convolutional CNNs, what type of features are typically captured by shallow layers, that is the early layers and deeper layers? Which option would you pick? Hmm?
Option B.
Option B, right? That is low level features such as edges and textures in the shallow layers, and then high level features. So there is something called receptive field of a neuron in CNNs, which basically shows, describes at what, how much area of the input region I'm actually capturing. It, in that neuron. So in the early layers, I'll be looking at very local regions, right? Just 3x3 filters and so on. So in the first layers, I am doing seeing 3x3 region. Okay. So here, in the first layer, I would be seeing at 5x5 only 5x5 region, right? And get my outputs. So I'll be looking at very local things, which is like edges, colors, and these kind of things. Later ones here, when I'm doing the same 5x5 operation again here, I would not just be looking at just 5x5 here, right? It looks at a much bigger area than 5x5 in the original image. Mm, mm, so the number of input pixels from the original image that are contributing to this pixel here is much more, right? So finally, starting from 32 cross 32, if I'm coming down to like 3 cross 3 feature map, that means each pixel is looking at say 10 cross 10 worth of pixels, right? Actually, that's even more than that. But yeah, I hope you get a sense of it. So that is called something as a receptive field of a neuron. Like what is the input area of the image that a particular neuron at a particular layer is looking at. So with the depth of the network, like the deeper the layers, the receptive field of that neurons are higher. So it would be looking at capturing global attributes. So that is why the end of the last layers of the neural network can recognize classes, but not the early layers. Okay, that's pretty much the questions content I had thought of discussing. So yeah, this will come back later, but yeah. So for a classification task, this is how you would usually design a network, right? I have convolutional layers, I get this feature map, then pass it to feed forward neural network. So this is classification where I want to associate one label to the whole image. Like I have a 200 cross 200 image and I want to associate it to say cat or dog. I want to get one prediction, right? So suppose I have 4 classes, 4 different animals. I want to recognize which animal that is and do that. But there are other tasks like segmentation and so on, right? Where in segmentation the objective is to associate one pixel for every one label for every pixel, right? If I have 200 cross 200 input, then I want an output which is also of a dimension 200 cross 200. Say, even for a simple foreground background task, so there's a cat and then there's background, right? I want to associate each pixel and identify whether it is foreground or background. So there my output dimension is same as the input dimension. That is, if I have 200 cross 200 pixels, I want 200 cross 200 outputs where each one is labeled 0 or 1. It's like a binary map I'm trying to achieve, right? So to do that, so how do you think you should design your network? It's like for classification you have convolutional followed by fully connected layers, right? What kind of change would you want to do in this network so that you can learn the network to do semantic segmentation? Can anyone like guess how would you design the network in for such a problem? Just think about it. How would you change the design of the neural network architecture? What kind of layers would you want to use? 3 channels. Output will also be usually one dimension output, right? Or even if I say 4 cross 1, 4 classes are there. 4 classes, it will give probabilities for the 4 classes, and then you pick one of them. But here I want to get the same height comma width comma 1, say to do foreground background classification. So what is the design change you would do? See where classification. So will I need feed forward neural networks to do this, or can I just do convolutions? So what is the goal? I want to preserve the spatial dimension, right? So suppose I just keep doing this, like I have 32 cross 32. Say I do the padding so that I still have 32 and so on. So I start from 32, then I have to keep 32. I keep doing this throughout the network. Then finally on the last layer, I just put like one fully connected layer over each pixel. Like, so at every spatial location, I would have so I start from what, 32 cross 32 cross 3, right? Then I pass it through some filters. Say I retain the spatial dimension. I get 32 cross 32. Say I use some 32 filters, and then from here I again do convolution. I again use 64 filters, suppose. So I do this. I pass it through 4 convolution layers, and I have got a feature map of this dimension. This is, I pass it through what, first layer, then I get this, then I pass it through the second layer, I get this, then I pass it through the third layer, I get this. So now say you can do n number of layers depending on this, and finally I want 32 cross 32 cross 1, suppose, final layer. So what can I do so that I can come from this to this? But I don't want to do that crazy flattening the whole image, getting that right, because that is practically impossible.
We can do depth-wise convolution or something like that. Like 1 cross 1 cross 128 filter you will take and convolve.
Yes, correct. So I do 1 cross 1 cross 128. So in that, what am I doing? So the filter size is 1 cross 1. That means I'm looking at only one pixel at a time, and combining values across the depth, that is 128 dimensions, and then that will give me out 32 cross 32 dimensions, right? Suppose I have instead I want to do C classes, then it would be it would be 1 cross 1 cross 128. This is the filter. So oh yeah, in all cases I would have some number of filters also, right? So it would be 3 into 32, right? 3 into 32, then this would be 32 into 32, and then 64. So this is the filter size, and the last one is the number of filters. So this would be the filter size, and then last one would be the number of filters. Okay, no, I think I messed this up. Not right. Anyway, okay. Yeah. Yeah, anyway, you get it right. Passing to 1 cross 1 convolution, combining all the 128 elements, and then I get one output. So if I want C such things, I would do pass it through C such filters. So this is what filter dimension. C such filters, and I would get this. So once I do this, so this then I put that normal probability, put the softmax function, and get a prediction for which class it belongs to. So these things are called as fully convolutional network because I don't have any fully connected layers, right? So it is called, they are called FCNs, or fully connected, which is usually used in segmentation problems. And another way this is done is, like, this is a high level idea. So there is something called like UNet architecture, where so here I have retained the spatial dimension, right, 32 to 32, but then this is yeah. So the requirement is that my input dimension should be equal to the output dimension, but these intermediate steps is not, it's not necessary that I need to keep it as 32 cross 32, right? To understand what is there in the image, like to associate that this is a cat and this is like background, this is a dog, I still need global context, right, not just pixel wise information. Because just pixels, looking at pixels is just color, right? I am looking at only local regions by doing this, but I also want to look at it, what it means globally, in order to, you know, associate a particular pixel as cat or dog, right? Like a white pixel can belong to background as well as like to belong to a sky as well as the fur of the cat, right? But you just based on color, I can't color, or even looking at a 3 cross 3 patch, I can't associate it with a class that easily, right? So for that, what is done is, you similar to what we do in convolution, the normal classification type. So you do downsampling using max pool layers. So starting from 32 cross 32, I can go down, like go down to say 16 cross 16, 16 cross 16, and then like 8 cross 8, 8 cross 8, and so on. 8 cross 8, say, go down to like 4 cross 4 in this fashion. So here I have increase the receptive area of these neurons, and able to look at what is there in the image globally, so that I can associate what is there. So these are downsampling, like, convolution layers. Then they introduce something called upsampling layers, where you go from say 4 cross 4 to 8 cross 8, 8 cross 8 and 64, so like just retrace your spatial dimensions back. Then I go from 16 cross 16 to 8, 16 cross 16 to 32, and the number of channels can vary, you can design it however you want, but basically upscale your features. And then you can come back to this 32 cross 32, and then you do the number of, come back to whatever filters, the number of filters you can set it as C based on what you want. So these is called as what you upscale, you upscaling layers, these are. And you come back to the original dimension and then do your classification. So this is like the design change for the task. It's just an example of how you design neural networks for the specific task in an optimal way. So like one common thing that is done is like you have lots of networks that are trained for classification tasks, like say they've used ImageNet data, which is like billions of data, and I don't know what, basically huge amount of data, and you've trained it to learn to classify like 1,000 crazy classes. So that model already knows like a lot of details, right? Like to extract all these edges, colors, textures, everything, and give some important, extract some important information from that. So you can start from that and extend it to a fully convolutional network. So this part of the network would be there, right? This part of the network to get this. So I take this, like I just remove. So this is the full, like the feed forward part. I just get rid of the feed forward part. I use only the first part of the network, which is just these convolutional layers, right? I just use these convolutional layers, like say till I get that 8 cross 8 image, and then I add newer layers, right, for these up convolution layers. Yeah, there are different names for this: deconvolution, upscaling, whatever. So I can use the base, like the downsampling part from a classification network, and for the upscaling part I add new layers, and I to train it for segmentation I just learn the newer layers without update. I mean, I can update the older layers and learn the new layers, but it's a much better start than doing it from scratch, right? Because you are leveraging the information you already know, like the good features which are learned during classification. So this is, I mean, adapting old networks to new tasks is called fine tuning, because you're starting from some learned weights already. So it's fine tuning, and then fine tuning plus we're adapting for a new task altogether here by learning some extra weights. So yeah, some sort of transfer learning. These are called, where you make use of existing information, existing weights for a new task. If it's just classification, I start from those weights, keep the network as is, or just change that last layer, right? Where it is. So initially I've learned for 1000 classes. Now I want to learn for just 200 classes, which is some altogether new classes. Then I just replace the last layer and then tune the whole network and the new layer. That is transfer learning in within classification. This kind of adaptation is called is also transfer learning, but to a different task also. Yeah. So okay, then that is pretty much what I have to cover for this class. If you have any questions, you can ask. Questions, doubts.
Ma'am, and where can we find more questions for practicing for the exam and things like that?
Oh. Uh, you can see the previous year stuff, right? Is it the same content?
Maybe the last year it was changed already.
Like the
Syllabus was
assignments are all the same, is it?
don't know. Just check it out.
You can check those, right? Like those questions from the past few years, which yeah, there will be some standard books from which you can solve, but you will have to tailor and look at them specifically, I think. But I feel what they do in your class and your assignments, this should usually suffice. From what I know, the like that homework questions which you get, right, assignments which you submit, those are MCQs, right? Which mostly solving MCQs or some numericals submit, they are pretty extensive, which cover a lot of topics in which are present in the course. So if you are, can extensively be able to solve those, that should be good enough. The lecture content versus this, I'm content with this. It's more than enough, I would say, to be honest. You train yourself to get used to that kind of thinking rather than, be able to find more questions and solve them. Yeah.
Ma'am, and I have one more question. Like in these lectures, this week and with this week lectures especially,
Mhm.
there are many architectures like ResNet and squeeze excitation blocks and many other architectures we are learning.
Oh.
So in order to apply this into some practical things, so should we do some kind of projects or uh, how can we get some understanding on these things so that if I am given a new task where I have to apply some practical application, I
Mhm.
should be able to figure out what kind of model should I apply, like should I take some pre-trained models or not. So these
Hmm.
kind of things, like how can we acquire this skill?
Yeah, that's a good one. So you can, yeah, this is obviously you learn theoretical stuff in this course, right? Like the basic building blocks of neural networks, what kind of layers, all this is there. Um, and yeah, these notebooks, everything are kind of simulated scenarios where you see how to put them in this. But for practice to put, you can try out some like challenges on Kaggle, I would say. Those that would be very realistic, right? You know Kaggle? Have you heard of it?
Yes, ma'am. Yes.
Yeah, you can pick. So there would be lots of vision tasks in that as well. Even like even if it is simple classification, segmentation, and so on, building that whole pipeline from scratch. Like don't use existing notebooks. Just take the data, and from scratch try to build your networks and try to learn. Like pick some small data set which has a few, say, 100 200 images, which you can actually run on Google Colab. So these network designs which are there, right? Yeah, ResNet, SqueezeNet, and so on. So you can use different architectures there and try and analyze yourself for that specific. Just take one data set and analyze different attributes for it and so on. And you'll also understand how to build like the data pipeline model, like end to end manner, right? In reality, we get data in like very different forms. You need to like create that data. So much of this ML work actually goes into building proper pipelines to make it work, like creating that data pipeline. So I think that would be a good practice. Like there'll be many such nice challenges in that. You can start from simple classification segmentation where the problem is very well defined. Like you know how the final layer should be, what the dimension should be in classification segmentation, such tasks, right? But in things like object detection is a little more involved because it's not just images something, right? You have to get bounding boxes, and you don't know how many boxes are there. Say if there are five objects in the image, I should get five predictions, like five coordinates, sets of coordinates output, right? So here the final output changes, it's not fixed. Do you understand? So how would you design something so that you get what you want? This was one such example what I showed, right? How to change classification network to segmentation task. So if it is object detection, also you can start, you can start from an ImageNet trained model and still build an object detection network, but you should be able to determine what the outputs are. If this is my number of outputs which I want, how do I design the architecture, such things. So start simple and you can pick harder problems with time and play around with it, I think. Obviously such things would have been solved, someone would have done, but still attempting to think and see how to do these designs would help you, I think, like, so that you can think on your own based on a new problem. Yeah, it's just experience, right? You've seen how people have solved five different problems. Sixth problem would be like some combination. You pick up ideas from different places, put them together, so that you solve that new problem. It's pretty much, most work is pretty much that.
Thank you.
Okay. Okay, then thank you everyone. We'll meet next week. So how was like today's session? Any feedback? Do you want me to do anything different from what I'm currently covering, or if like any specific things if you want me to do, you can tell so that I can plan it that way. Or like even if you have need not be like say this week's content also. uh, so something in this week which you did not understand, next week if you tell, I can prepare that specific part and explain to you later or something like that also for a few minutes. If you can name some particular part which was hard or something like that. If not on that day, then later week at least I can present that part if required. Otherwise, I would just pick something, some topic and a few questions this way and go ahead this way. Anyway.
One thing I found is the notebooks that you have discussed today and the initial questions on the deep learning part, the same questions were discussed by the other layer also. So it is some kind of a repetition kind of. So maybe can skip some of them if it is already discussed in some other session.
Yeah.
That would we can cover something more new. That would be more beneficial.
Okay, fine, we'll try to do that. But yeah, so the point of this thing was assuming different you guys will attend one of the sessions and not all of them. That's why the questions are usually shared.
Okay.
Yeah, but yeah, fine, we'll see. We can have like more number of questions and split it also. I can discuss with the others. But, okay. So yeah, the notebooks are the same, but questions we can maybe try to do something different. We'll see. Okay. Okay then. Thank you. See you.
Ma'am, and regarding the topics that you have asked, maybe some kind of some important networks like one is ResNet, like the other is this efficient net. If you can actually tell the motivation behind these things and why these things work like that.
Okay.
Style.
Sure. Yeah. I'll do
Some of the major networks, not all, but
yeah. Sure. That was actually in next week's content, right?
yeah.
Yeah.
This is the week, so this week it is going on.
Okay, fine. Yeah,
Lectures are-
I'll discuss the architectures in detail. How actually those early networks, right? They all were, the trajectory is so good. Something they addressed, some drawback, which was the origin for designing the next one, right? I'll look into that, go over it and present it that way, sure. Yeah.
Yes, thank you.
Okay, thank you.